Hi everyone, I'm Silvia Gasparotto. I'm a PhD student at IFA in Barcelona, and today I'm going to talk about cosmic birefringence and gravitational waves from cosmic defects. This talk is based on this work here that I've done with my collaborators Riccardo Ferreira, Takashi Ramazzo, Ipei Obata, and Oriol Puyolas. In my talk, I'm going to introduce briefly cosmic birefringence, both from a theoretical perspective and the signal. And then I will move to the focus of this talk, that are domain walls as a possible explanation of the signal. Then I will explain the second observable such a scenario, that is gravitational waves, and then I will touch on other types of network. Let's start with axion birefringence. So in this talk, we consider axions, that is a well-motivated and most studied extension of the standard model. And what we have to know is that an axion field is a pseudoscalar, and it can interact with the electromagnetic tensor through this interaction term here. And the important characteristic of this talk is that this term is parity odd. As we can see, if we write it in terms of the electric and magnetic field, this can be written as E times P. And because the two transforms in a different way under parity transformation, this term is parity odd. So it shouldn't surprise us that this term modifies the Maxwell equation in a parity violating way. And in fact, one finds that the dispersion relation for the left and right-handed photon are different, as we can see here. So this means that the phase velocities are different, and the modification is proportional to the strength of the interaction and the time derivative of the axion field. The additional effect is that if we have light that is linearly polarized, so it can be equally decomposed into left and right-handed photon, because one polarization travels faster than the direction of polarization rotates. So we can use any source of linearly polarized light to look for such an effect. And in this talk, we focus on the CMB for mainly two reasons. First, the CMB are linearly polarized, and then it's the first light that we have access to. So even if the axion field evolves very little, or the interaction strength is very small, because the effect accumulates over time, maybe the CMB is the only place where we can look for such an effect. So how do we look for this effect in the data? So in a parity invariant universe, we have that only the parity even combination of the E and B modes are non-zero, so in particular CEE and CPP. But if the original polarization gets rotated, this induces a parity of the power spectrum. Particularly, we have a non-zero EP that follows this formula here. So one can look in the data and fit them to find the value of beta, also known as the birefringence angle. So if this beta is uniform over the sky, this is completely degenerate with a miscalibration angle. This was the main difficulty of this search, but in 2020, Minam and Komatsu developed a new method to measure the birefringence angle and the miscalibration angle independently, and they claim that a value of 0.35 degrees. After the result, also other people did the analysis, and all of them confirmed to a value of birefringence angle of the order of 0.3 degrees. Moreover, the signal looks frequency independent. So the status quo is that a zero value for the birefringence angle is excluded by more than 99%. So if the signal is there, it's important to know what can originate such a signal. And as I explained before, the presence of an axion field can easily do the job. So in this case, the total birefringence angle is given by the integral over the line of sight of the difference in the phase velocity. And it turns out that it depends on the strength of the coupling and just on the difference value of the axion field at the emission and the observation point. So in the case of CMB, we have to compute the different value from the last scattering surface and today. And here is where the model dependent enters, because the axion evolution depends on the potential of the axion, so in particular on the mass of the axion and on the initial condition. And in general, there are two main scenarios that can explain the signal. One is when the axion field is uniform over all sky. And this is the typical scenario of misalignment production, or also known pre-inflationary scenario. This is typically the case for axion dark matter or axion dark energy. And this is the parameter space that can explain the signal. So in particular, we see that an axion in a very broad range of masses can explain the signal from 10 to the minus 40. So here in this regime, axion can explain the totality of dark energy, whereas for masses bigger than the Hubble parameter today, here the axion field would behave as dark matter, but it's bounded to be less than 1% of the total dark matter energy density. In this scenario, small fluctuations are expected from the early universe, from isotopic curvature or adiabatic perturbations. So in this scenario, the isotropic signal is the dominant one, whereas the scenario is different if the universe is filled with a network of cosmological defects, as it can be the case for the case of axion. And this is what I'm going to focus now. In particular, I will consider domain walls. So domain walls are field configuration that interpolates between two degenerate minima. And they happen when our vacuum has different disconnected minima, as it is the case for axions that have a cosine potential. So this number here gives the number of different minima, and Fa is the decay constant, gives the distance in field space between the different minima. If the initial value has sufficient diffusion, so it has a different value in different part of the sky, it happens that when the Hubble parameter becomes of the order of the mass of the axion, the field starts evolving and starts oscillating around the closest minima of the potential. So in particular, the field relaxes on different minima on different parts of the sky, as shown in this picture here, and a domain wall network at the interface between one region and the other. And the domain wall is characterized by the typical width given by the inverse of the mass of the axion. So after the network of this domain wall is formed, this soon reach an attractor regime called the scaling, in which we basically have one long domain wall per Hubble volume. And this is represented in this plot here, where we basically have that the outer layer is represented the network at some early redshift. And as we go along the circle, we encounter many domain walls every time we pass from red to blue. And as the universe evolves, we move to the center of the circle. And if we, for example, consider a different redshift here, we see that we encounter less domain wall because the Hubble horizon is bigger. So in this regime, the energy density stored in the domain wall goes as 1 over T, and it depends on the tension of this domain wall. So we see that the energy density of the network decays slower than the background, for example, for dark matter. So this means that the relative importance of the network grows over time and eventually tends to dominate the total energy density of the universe. So this is a situation like a dangerous situation, and cosmology tends to avoid it. And there are two main ways in which one can avoid this situation. One is the collapse. So if there's a difference in the potential between these two minima, this exerts an external pressure and makes the network collapse. Or the other situation is that the tension of the domain wall is small. Or one can consider a mixed situation as we do. So let's go back to the case of cosmic birefringence. We wanted to explain the isotropic signal we have from CMB. So as before, we have to take the difference of the field value from the last scattering surface and today. The point is that in this scenario, we have that at the last scattering surface, the field has different value as we move like as we look in different direction. So for the isotropic part, we have to take the average value of the loss of scattering surface. So in the case of two minima, for example, if the initial distribution is symmetric, we have the half of the probability for being in one minima and half of probability to be like in the other minima. So the average value, let's set it to 0. But then our local universe selects one of the two. So when we take the difference, we have an isotropic value that is already of the order of the signal we have some from CMB, and it depends on a parameter C that is typically over the 1. But then the point is that because of this anisotropies at the lasso scattering surface, this would also imprint some typical anisotropies in the birefringent angle described by anisotropic power spectrum given by this formula here. So what's important here is that while the total amplitude of this power spectrum depends on the square of the isotropic birefringent angle, so the two are related, and the spectral shape instead is given by the power spectrum of the field evaluated at the emission point, so in the case of CMB. We have performed a numerical simulation for computing the power spectrum of a domain wall network, and this is what I'm showing here for two different choices of the initial condition. But the important point is that there are some universal features of this power spectrum. First, it has a peak at the horizon sides. And the reason is that we have maximum probability of finding another domain wall at the horizon distance when the network is in scaling. And then it has some decays when we go to higher kappa that has this typical decay that is the same, it doesn't depend on the initial condition. Also, an important remark is that, well, the power spectrum of the anisotropies do not depend on the energy density of the domain wall. Okay, then to actually compute the power spectrum of beta, one has to perform this integral here, and after doing that, this is the result. The polarization of this in B are not just originated from recombination, they are also generated at a later time at the reionization, as shown in this plot here. So we can separate the birefringent angle generated from recombination and the one generated from reionization, either for the isotropic angle and also for the anisotropic angle. So in the case of a reionization, we have to evaluate the power spectrum at the reionization instead, and this is the power spectrum for the anisotropies that we get. Another important thing I haven't said before is that so far we just have a measurement of the isotropic rotation. We haven't measured the anisotropic one. We just have upper bounds on the amplitude, and this is what is shown here. So these are the order of 0.01 degrees for a scale invariant power spectrum. So one should perform the analysis using this spectral shape. And another thing is that if we apply this bound naively to the case of the power spectrum from reionization, we would say that a presence of domain wall is excluded. But the point is that current analysis assume the birefringence is generated from recombination. So if one does not assume that, the bound relaxes by more than 3 orders of magnitude, as pointed out in this recent paper here. The interesting thing is that by measuring the birefringence angle from recombination and reionization, either for the isotropic and the anisotropic one, we could probe the evolution of the domain wall network. This is shown in this picture here. So basically, if we have, for example, the domain wall that is present at recombination and also the reionization, then we would expect anisotropic birefringence angle that is that is similar for the two epoch, and it is different than zero. And then a power spectrum that has a double peak, one corresponding to recombination and the other from reionization. Then if the network annihilates between recombination and reionization instead, we would have a different value for the beta from recombination and reionization. And then we would have the power spectrum that has just the peak of recombination and nothing for reionization because the network has gone already. Another option is that a late forming domain wall. So if the network forms after recombination, at that point we would have again the same value for the isotropic rotation from the two period, but we have just the peak of the power spectrum at the reionization. And the last case is where the domain wall forms after reionization. In that case, like the situation is very similar to the case of a uniform axion that I explained at the beginning. The point is that if a network of domain wall is present, this would also generate gravitational waves. And the idea is easy to understand. The point is that these domain walls are not just straight, but they have some typical curvature of the order of the Hubble horizon. And as they move, they generate quadrupole moment, so they generate gravitational waves. And the total energy of the gravitational waves in scaling, one finds that it is proportional to the tension of the domain wall. And then what we compute from our numerical simulation is the spectral shape of this stochastical gravitational wave background. So one finds that if we look at the abundance of gravitational waves, this grows over time. So the late time emission is the largest contribution. And we assume that in the case of annihilating domain wall, the spectral shape is given by the network in scaling, and the peak corresponds to the horizon size at the time of annihilation. So we use the spectral shape to put a bound on the tension of the domain wall. The presence of the stochastic and gravitational wave background would generate B modes in the CMB, and since we haven't seen them, we can use it to put bounds on the abundance of the gravitational waves from a domain wall. This is what is shown here as a function of the temperature of the annihilation. And then we can translate this bound to a bound on the tension of the domain wall. Then let me go very quickly to the last slide that is about other types of network. So basically in the case of axions, do not have just a domain walls, but also cosmic strings. And the case of cosmic birefringence coming from cosmic strings was considered in this paper here. And they consider like a loop crossing model. So the idea is that every time a photon crosses a loop string, this with an extra flip of the polarization. And this is the effect that dominates for the anisotropies at small scales. They were saying that a non-detection of the anisotropies is incompatible with the isotropic signal reported from CMB. But we believe that in their model, they are missing some additional contribution that would mainly change the birefringence angle on large scale, so affecting the isotropic rotation, whereas it would not change the power spectrum at smaller scales. I hope to have motivated as the cosmic birefringence can be explained by any axionic network, and this scenario would soon confirmed or ruled out by future analysis of the anisotropic birefringent angle. Then I explain as we put bounds on the domain wall tension from B modes, and then I'm happy to talk with you about like other observational effects of this scenario, or maybe the imprint on large scale structure of this scenario. Thank you for your attention and looking forward to discuss with you.